are you guys ready? Ready to go?
We're about to go on air.
Go story.
No stories.
All right, we're on the air.
We're on the air with this actually really cool picture. So, yeah, with that.
Okay. Okay, so just go in? Okay.
You're the chairman.
Oh, yeah.
Chairperson.
Chairperson.
Or just chair.
So weight agnostic neural networks. It's called weight agnostic because you have one shared parameter in the entire network. The idea here being to construct neural networks that have this one shared parameter that are also minimal and they're like connectivity. So let's see here.
You say minimal in the context, does that mean they're sparse?
Yeah, sparse. Yeah,
Okay.
that is another word for sparse.
So
Yeah.
the sparse networks where you really don't train or tune or anything.
Yeah, everything has the same weight. Every connection is the same weight.
And,
Yeah,
the,
yeah.
weight, and the weights are initialized but not trained. I mean, the weights learned.
Though the weights are not learned, the idea is to actually try to learn a neural network that sort of by its structure alone can actually perform a task.
So that means the learning is the structure.
The learning is the structure.
Okay, so
Yeah,
there's
exactly.
learning going on. It's kind of like what we do in our biological models.
Yeah, I think it's
Yeah.
exactly identical.
Okay.
In many ways.
That's how we
The
model.
method is totally different.
But that's how we've modeled our neural systems, is we just assume they're binary weights, and all training is in the network architecture.
Yeah, exactly.
So
And
this is basically the same idea.
yeah, and so they'll actually run these, they'll sort of like run their experiments or run these agents with this neural architecture and with sort of just a varying range of like weights and show that it'll actually work like irrespective of the weight that's actually given to the network. Does that make sense?
Yeah.
Okay.
But in some sense, I'm sorry, I didn't read the paper, I didn't. But if I think about our previous work in
Mhm.
brain modeling, this would not be a surprising result. That if you are relying on a distributed representation, then it's the distributed representation which carries the meaning, but
Exactly.
not the weights.
Yeah, that's actually what they're trying to get at.
But that should be obvious in some sense. So did they approach us like that should work, and then we're just proving it?
No, in the machine learning community, that's not at all obvious.
But they did think it
spend
was.
all of backprop is about.
I understand, but that's because they haven't thought about representations being
That's just not
RCS.
obvious for them.
But if you are doing distributed sparse representations, then it should be obvious.
Yeah,
I would say that the set of people for which this is obvious in the world is very small,
Okay.
like really.
But we
I mean, for us, it's.
we understood our
yeah.
first principles. No one had to tell us, and we didn't have to test it. It was like, oh, yeah.
But even in neuroscience and computational neuroscience, they still have scalar weights and they still
Yeah.
think about.
Well, I can see where they're coming from. That's true.
Yeah.
But once you've accepted that you have sparse connectivity and sparse representations.
Yeah.
Which they don't generally think that way, but once you've accepted that, then it follows naturally.
Yeah, they actually gave this sort of biological like motivation with respect to animals that sort of know how to do things at birth, sort of suggesting that potentially there's what they called like strong inductive biases and like the connection.
But that's different. That would be not learned, right?
Exactly, no, that's like the point. There's like sort of like connections.
Yeah, maybe there are two independent issues here. One is the values of the weights.
Yeah.
And they're all identical here. And the other is the structure and how you
Yeah.
learn the structure. And you're talking about the inductive biases in the structure.
Yeah, exactly. Inductive bias. In this case, the structure is not learned at birth, but sort of like learned by like evolution before the thing was born.
Yeah.
But yeah, so they kind of go at it with this motivation that there's like something inherent, like in the structure that can perform these tasks. So they do this in a reinforcement learning setting. So they have like three examples. One is this bipedal walker. They have this. So basically, this walker is just trying to go as far as it can, as like efficiently as possible to
You can see
to
this
minimize its
live
sort of,
at that
So we're
URL
doing
right
this
now.
with an evolutionary.
That's in chat.
yeah. So this will be done with an evolutionary. I'm just sort of explaining the problems that they actually did it on. And so I'll kind of get below. I'll get to like how they actually arrive at these networks in like a little bit. But just kind of explaining the problems.
This is a great
and
way
then
to
there's
publish
like
a
a car
paper, by the
racer
way.
just trying to like stay on the track as long as possible. So I think these are like fairly like standard like RL games. that people try to train on and sort of kind of compare the performance. So they'll end up actually showing that, like with these weight agnostic neural networks, that they can actually do fairly well in these games, and almost like match state of the art. Like once they like tune this like one weight parameter, which is pretty surprising.
Are you gonna explain what that one weight parameter is?
What the one weight parameter is?
Yeah.
Well, the one weight parameter is just like, I mean, imagine just like a sparse neural network and all of them have the same weight parameters. So the idea is, the thing is, it shouldn't really matter like what the weight parameter
Yeah, I was
is.
gonna say, if they don't, if they're all the same, what difference does it make?
You can still make it bigger or smaller.
Yeah,
They're all
but
the
in
same.
theory, that doesn't really change anything unless, I guess you say it's changing relative to some sort of threshold in the neurons or something like that. I mean, if I multiply everything times 2, it's not gonna really change anything, the information conveys the same.
Biases in this network.
In a nonlinear system, it does. In a linear system, it won't. But in a
Yeah, I guess I'm saying relative to the nonlinear function of the neuron, it would make a difference, but that, you could just as well say, I'm leaving all the weights the same and I'm changing the nonlinear function of every neuron, right?
Yeah.
It's sort of like changing our dendritic threshold.
Yeah.
You know, it makes a difference. Obviously, if we give a 1 value to every synapse, and then the dendritic threshold is gonna be different than if I give a 0.5 value to every synapse.
Yeah.
But so I would view that less about a synaptic parameter. I would say that's more of the neuron parameter as opposed to synaptic.
I'm not exactly getting that, but yeah, it shouldn't matter the weight. You're absolutely right about that. They do show that, but regardless, you technically can do that one weight to optimize for the one test.
Yeah, I see why it makes a difference relative to the threshold of the neuron.
But they don't really care about that. They basically just like want to show that even without like even just any random weight should still like perform very well. Yeah.
Are they using ReLUs?
Yeah, they are. So I'll mention them like a little bit. Yeah.
They're actually also optimizing, they're choosing random nonlinear activation
Oh.
factors, so you can see all nonlinear random interruptions. So that's why I think the value of the weight makes a difference, but each one of these functions will have a different kind of nonlinearity.
Yeah. So I get that, and like the actual like training is the next thing anyway. So scroll down a little bit. They have like a nice sort of diagram that illustrates how they actually kind of.
That's not the thing.
That's in the paper.
Shoot.
Yeah.
Oh, cool.
Oh, okay.
Yeah, it is.
I'm saying, I was skipped
You're
that.
just looking at the odd pages.
Yeah.
You put it in black and white, that's why you remember.
Okay, so they start off with just a very like the bare bones of the network that they actually need. So however many inputs that are given in the RL task and the number of outputs that they actually need to give, and then just very, very sparse connections between those things, and even like leaving out some of the inputs.
They randomly connect.
I will be just depending.
Yeah, so these are just chosen randomly. So this is just sort of like, this is an evolutionary algorithm. So this is just a sort of like initial, like bare bone minimal population, just to say like, here are outputs and here are inputs, and maybe here are like a few connections between those. And so then they'll sort of take these networks and then they'll initialize the weights. They'll sort of like use the same like 6 set of weights throughout the entire, or they're sort of like, they'll test those networks with W is equal to +2 and then see the performance, W is equal to +1, test the performance, and they'll do that with the same number of weights for the same, like for each network in the population.
So they're actually using the weight value itself as part of the parameter of the evolutionary algorithm.
They're not trying to use the weight as a parameter. The reason why they try to do it in this way, using like all
You said
6.
they try +2, then they try +1, and
Yeah, for the one network. The idea being here is let's try like a wide range of weights and then take the average performance and then make sure that this network can perform well on a wide range of weights.
oh, I see.
Yeah, exactly. So then they'll do that for every single sort of possible network in the initial population. They'll rank its performance sort of by like its the max performance of one of these networks, the average performance of all the networks, and then they also rank its complexity, or just sort of like which I think they didn't describe exactly how they do this, but it's sort of based off of how many connections it is, sort of like how sparse it is essentially.
So lower is better in that case?
Yeah, lower connectivity is better. Exactly, yeah. So the idea being here that the evolutionary algorithm will also try to select for like sparse networks, and not just sort of like make just very complicated structures and whatnot. So, and then after that, they'll sort of like take their, I guess, best few, and then they'll sort of vary those. So they can vary these networks in essentially like one of three ways, which I think there may be a better diagram of how they vary it. Okay, yeah, so here are the three in the middle. So they can either insert a node between an existing connection, they can either add a connection between two existing nodes, or they can change the activation of a current existing activation. And so they actually have quite a few activations that they list here, like linear, step sign, cosine Gaussian, tangent sigma.
Would that apply to all units or just that particular?
No, they would just change the ones. So these are like these are the changes that they make to the winning networks are very, very small. So it
But
only
by
change-
changing the activation, no longer, so then different units in the network have different activation functions.
Yeah, exactly. Yeah, I mean
Right,
these
so it's
two.
not, and now it's no longer purely, that's a form of learning, right? That's a form of, if every unit could have a different activation function, then you're training on that.
Every unit could have a different activation function. What do you mean by every unit? I mean,
I'm
in
just
this
saying,
case, it's only
you're
these
just
two.
changing the activation function of that one unit there, and other networks have different activation functions that are being changed differently, right?
Other networks.
Other
Yeah.
units.
Other units, I'm sorry.
Oh no. So I mean, when you
This
say
is not global to the whole network.
no, there's not global. These are very like local
Yeah,
changes.
so
that's
then,
what he's saying.
different units would have different activation functions.
Yes.
So that then becomes the unit by unit parameter of the network.
Yes. A unit by unit. Yes.
Yeah, I mean,
Some of
so-
them may not even have activations too.
I think it's just linear. I mean, you can just think of it.
I'm just
Yeah,
pointing
yeah,
out that this adds another level of complexity, which we haven't thought of, and I don't think neurons think about.
Oh, yeah,
Where you're changing on a unit by unit basis, the activation function of different neurons.
Yeah.
That's an odd way of training a network.
You
It
have
is
different populations.
very odd.
Yeah.
I also thought very strange. It's very.
You have different cell types though, so.
Yeah, but not like this. I mean, we have different cell types, but, I mean, that's a much more structured thing, and I'm just saying, you're right, it is, but that's still not how I would do this. I
Yeah,
would do
and
this.
pyramidal neurons basically are parameters.
Yeah, exactly, that's how I view this, and there are different types of pyramidal ones, but in this kind of network here, like we mentioned, some pyramidal neurons may behave differently if they're doing a grid cell function or something like that, but they're not doing anything like that, they're just doing this is your classic neural network, type of.
But in the sense that you choose whether to synapse close to the body or along the genetic tree, those could kind of.
Yeah, but if you did that, then if you wanted to introduce that level of realism, then you say, okay, a neuron basically has an extra state, which is it's a predictive state or a non-predictive state. And on the distal synapses, that doesn't cause a cell to fire. And they're not introducing that complexity here. They're just saying, they're just changing.
But this could be like a stand-in for that
It
complexity.
could be. I'm just saying it's pretty unusual.
So, I mean, you could say rather than using different activations, use a different characteristic that you just described.
Yeah, but it
More closely
would
aligned.
For the
require
subscription,
much
Philip.
more thought than what's going on here. Seems like.
Right.
Yeah, but this is a machine learning paper, they're not trying to
I'm
match
just,
pyramidal neurons.
I'm just surprised to see that. And when we said that
In the
there's
machine
only
learning
one.
setting and the neuroscience setting, or both?
Well, in the machine learning setting, because we said, first of all, you started by saying there's really only one parameter, but that's
No,
not
right.
true.
Well, it's the structure matched with the one weight. I mean, yeah,
If I think about a parameter, it's something I change to the property of the network,
yeah,
right? I'm changing this on a unit by unit basis. I'm changing the activation function.
you don't think that is like changing the structure?
No, to me, the structure is the graph.
Oh, I see.
Isn't that how most people would
Yeah,
do
I
it?
think so.
Yeah. And by changing not only the activation function, you change the activation as well. So you're actually changing, you're not changing the weight, but
Yeah.
that is not the weight, but that is
Yeah.
the activation. So the
Yeah.
values from the scalar values will be different.
Yeah.
I do agree with that. Those are like parameters.
It's like, yeah, you could justify doing this. I'm just pointing out the way, the way it was positioned as we're learning by changing the graph, which is these other ones, inserting an L.
Yeah,
But it's closer to what a classical genetic algorithm tries to do. You've got a topology that you can connect these things in some order, and you have some functional units.
I'm just, all I'm pointing out, Kevin, is this, I was surprised to see it. First of all, it conflicts with the way the paper was described, which is really, we're just changing the network structure, and there's only one parameter, and they're showing that one parameter
Yeah.
don't really make a difference. This is now making the network very non-homogeneous, heterogeneous. Every unit could have a different activation function.
Did they show that this is critical, this step?
That's a good question, actually. I don't think they explained that. That said, when I was using the word structure, they were using the word architecture. I don't know if that necessarily makes a difference. Like, I think they actually do view this as like sort of in the vein of changing the architecture itself and not actually changing the parameters.
I mean, think title earlier of weight agnostic, and they try to say, let's tune this network so that no matter what the weights are, we still get the results that we want.
Yeah.
Technically, that's what they're achieving, you know,
Yeah.
but the mechanism, the complexity of the mechanism, both topology and functional.
Yeah, but imagine if I did this and I said, okay, I'm not gonna do this activation function change. Every unit's got the same activation function. I would love to know what kind of results do they get with that? You know, is that sufficient where you're just changing these other things, where you're essentially changing the topology of the network, and that's the only thing you're changing?
Yeah, that would be interesting.
That's what
a
I
good
thought
point.
you were going with. By introducing this, sure, this is gonna make a difference, and sure, the evolutionary algorithm is gonna figure out different values that work better, but it kind of muddies the whole picture. It makes it very hard to interpret
Hey,
what's
Jeff.
going on here. You're adding an extra stuff, you know?
Yeah, that's a good point.
You guys hear me?
Yeah, Matt?
Hey, Jeff, somebody actually said something interesting in chat. You could might think of the different activation functions as being different types of cells, if that makes any
Yeah,
sense.
that's what
Yeah.
Kevin was saying.
Yeah, that's what we.
But-
Well, and Kevin, different parts of the cell, like different,
Yeah,
whether
we
it's
started first
maximal,
one, he
distal.
said, yeah, you could. I'm not against this. I'm just pointing out that it's, this is a huge change from saying we're just checking the topology and we're seeing how we can do it to topology. And now it just makes, so if it's very hard to interpret the results, it's gonna be very difficult to interpret the results if this is part of every experiment. If they did controlled experiments where they didn't change the activation, I think it's Supertype suggests.
So all the experiments, this is key for the paper changing the activation function, because they're trying to model like nonlinear systems, and they try to model a various bell network that you can interpret, so they can say, okay, I can get, I don't know, the inverse of the velocity and then pass through a 10H, and that's going to impact my my bipedal arc or somehow. So they're trying to model this nonlinear system with small networks, but they're not thinking about like simulating a brain or.
Okay.
Yeah, so I think this is something, I mean, if I was to give feedback to the author, it would be to really test the impact of this. Is it really?
But I think this is key to the paper. They're not seeing as just the structure, they're seeing as the architecture, and
Yeah.
these nonlinear functions, it's exactly what we want to model, that like each layer needs a different nonlinear function. I don't think they even thought about doing like ablation studies and removing that.
Yeah, I'm saying they should.
Yeah.
I know they didn't think about it, I'm
Well,
saying they should think about
So
it.
I was. it's
There's a
funny
question,
because-
is it the structure of the network, or is it really all of these, tuning?
Yeah,
Because you could also keep the structure being dense and tune all of these things, right? That's another possibility.
yeah. And how many different activation functions do they have, or is that a continuous range?
It's this right here.
6, 9, 12.
They've got a toolkit, a finite tool.
Wow.
But for each one, do they also change the parameters, like the sigmoid, do they change the,
I didn't check that. I would assume probably not.
there's just some standard thing?
Yeah, because then they would have another parameter. Right?
I think it would be a much more powerful result, not to take away from it, but it would be a much more powerful result. You could say, okay, just assuming a step function or whatever, pick one, the sigmoid, classic function. We could get great results just by tuning the connectivity of the graph.
Yeah, that's true.
That would be a more powerful result. And then you could ask yourself, well, how much does it make a difference if I use a different function? Can I get, and then you could ask, well, how much difference would it make if I allow the function to vary under the evolutionary algorithm? But right now, they're creating a new type of network, which I don't think anyone really understands or thought about before, which is fine, but it's just really hard to relate to anything else that anyone's ever done before. And it's really hard to relate to brains, so that's not their point. But
And I think the second question, what if you just change the structure? It's the same one we are trying to.
Yeah.
Maybe we should.
what's
add-
that? Which, say again?
If you can learn just by changing the structure of the
Yeah.
network, that's the question we are trying to.
Yeah,
answer.
Yeah, and that's how all of our brain modeling works. It's all based on that. With a more complex architecture and much, it's very different, but in the end, all of our networks learn by that method.
I was wondering if maybe try a shared weight methodology. Can also experiment. and
In
see.
the dynamic pruning stuff?
Yeah.
I think eventually,
Yes,
I think eventually we'll want to go that ties to this issue of can we get the binary weights basically.
Right.
Yeah,
So,
yeah. I mean, even if you're going to implement this in silicon or something like that, these changing activation functions adds a complexity that you really would not want to have if you could avoid it.
Yeah.
So the question is, how much are their results dependent on the changing activation functions, and how much are dependent on the connectivity changes? But it's a critical question.
But you could probably collapse all those into an activation that has 2 or maybe 3 free parameters, and then you can explore that space coherently. These, are just saying, I've got a graph bag, and these have certain functions. Some of them are symmetric, some of them are asymmetric, some are biased, some are not biased. But if you're looking to see how critical it is to have those extra degrees of freedoms, then if you have a functional representation of these activations, and then say, okay, let's clamp down, some of the degrees of freedom and see if we still get.
Yeah, I
results.
guess, yeah, but if you think about the future of this stuff, we really, really would like to, my mind's been in this already for years, maybe that's not biased. You'd really, really want to get down to the point where the only thing you're changing is the connectivity of the graph, and the weights are binary. That is that would be the ultimate goal in terms of implementing this stuff efficiently and fast and so on.
Yeah, I think I would be okay if they change the activation, but if it was global to the network.
Oh, sure,
Then
of
it's
course.
like,
Oh, absolutely, that's why I said the
activation.
second thing I would do is pick one activation function, and then pick another one, see if it
Yeah.
worked, and then pick another one, see if it worked for all of them.
Yeah.
Because I totally agree with that. And of course, that goes along with the weights, right? The weights, as I said earlier, the weights don't really matter. If they're all the same, it really only matters relative to the activation function. So you could say, let's just pick a binary weight and then pick the right activation function that works for the binary weight.
But it is interesting that if they can build something up from the bottom up, by using these operations in their genetic algorithm, that allows you to let something run, for a while and come up with, here's networks that work for whatever reasons against this particular problem domain.
Yeah, but again, our goal here is to figure out how to implement this stuff efficiently. I'll stick with my point. And my point is you would rather not have to have that. And we could come up with all kinds of architectures that allow you to do evolutionary learning and fine. I don't think the goal here is to solve this problem. The point in my mind of doing, I don't know what their motivation is. The point in my mind of doing this kind of study is not what's the best way we can solve this problem, is to say what is the most efficient, are there efficient ways of solving the problem that are different than people have been thinking about, that are very, very efficient. They're very, very efficient because they just you're just changing the graph function and the weights are all the same. It's basically going to binary weights, is what we're trying to do.
So I think this can be pitched as a significant result or very close to a significant result. And it kind of goes with what Kevin alluded to, how this activation function can kind of stand in for different dendritic integration zones. You can replace weights with some more complex neuron that has where if a synapse occurs on one part of the neuron, it's this activation function. If it's on another, it's like this other activation function. This is like a proof of concept that you can eliminate weights and just bring that in as a replacement.
All right, I agree, but also respectfully disagree. I think it's a very inefficient way of going about that.
Okay.
And it's confusing and it's hard to interpret, and it doesn't have that interpretation. It's separating from the biology. You can make that correlation, but I think it's just, if I wanted to explore the different type of neurons, then I would build these units to represent the different types of neurons or the different types of dendritic things, and then explore that as opposed to having 8 different or 12 different types of activation functions.
Mm-hmm.
So I mean, we can agree to that, what you said, Marcus, but I can also just say, because I don't think it's not the way you should. If I wanted to go build an efficient system, it's not the way to go about it.
That said, I do think that this is, like a super type pointed out, like the ML community doesn't necessarily sort of view like the connectivity as like an important thing, or like the fact that a lot of the information is put on the weights.
Mm-hmm.
And I think just with respect to that, maybe not with respect to individuals that already sort of knew that, like you said you've had this intuition for years.
Yeah, I mean, in the deep learning community, it's all about you set up this dense connectivity and then use backprop to tune the weights it's all about how you tune the weights really finely.
Yeah.
That's like the 99% of the deep learning community. So this is completely the opposite of that.
Yeah.
There's no, almost no backprop, I think,
Mhm.
and just structure and now activations. So it's
I think one value has not necessarily focused on what we're trying to do here, but for the ML community is, if this is a generative way of generating networks, and you set this as an evolutionary goal, and then you see, okay, are things naturally evolving towards sparsity? Are they naturally evolving toward small world? Are they naturally evolving
Yeah.
toward free scale?
Well,
This
they
is
selected
an
for
exploration space that you could set that as a problem and say, yeah, okay, these things
Yeah.
tend to fall into these basins of.
I got it.
well, they will tend towards sparsity because that's a constraint of that's a regularizer they use at their.
No, yeah, I understand.
And our point here is not just to do machine learning. I mean, look, they can do what they want to do. Our point here is to take what we know is true about the brain and try to figure out how to inject that into machine learning. So to the extent that we can look at something like this and not the fault that this research, but to say how useful is it for our goal? And I find that this changing of activation function makes this paper and this kind of results less useful for our goal. And we're supposed to put that bias on this. We're not just supposed to say, let's just explore the space of possible solutions. That's not what we're doing here.
But if you can look beyond the activation one and just look at the generative creation of things, and you put the constraints on that you want, you say, okay, it's gotta be binary, it's gotta be just the connections. This is a mechanism for going and exploring.
Yeah, I
some space.
agree. I was so excited about it until we got to start changing the activation function.
So,
So
can
that
I
messes it up.
can I ask a specific question? So they started with the minimal network.
Yeah.
How did they decide exactly to insert a node? What is their logic for doing that?
I think it may be like random. I think they like sort of randomly choose like one of the three: insert node, add connection, change activation.
Right, so it's a pure genetic algorithm in that
Yeah,
space,
so
it's unbiased.
Exactly. Yeah.
Yeah, so they randomly do that and then,
Randomly assign it an
For
activation
fitness.
if it's a new node.
okay.
Yeah.
And so it's a purely random search. There's no other.
I believe they didn't really describe actually their selection process in detail, but they made it seem as if it was like fairly random. But
Yeah, it says that they're using this well-established evolution algorithm NEAT.
Yeah, exactly,
Evolution
yeah.
algorithm,
Which
Which I guess
whatever I
whatever.
think about, but I mean, once you have, you develop a couple of these networks, then you do recombination, you do all sorts of other things, you do
Yeah.
algorithm to see, to drive the evolution, so.
Yeah. So I should say that there's already a bunch of stuff in deep learning that's doing that kind of stuff. It's called neural architecture search or AutoML and things like that, where they're doing genetics, roughly genetic style stuff where they're evolving the architecture and they do various ways of combining and splitting and adding and stuff like that. So this is kind of realized, and I think NEAT must be just another one of these things that they're using. But Google, you can actually subscribe to AutoML and it'll just do it for you.
Going back to the activation functions, did they report after they've trained these networks, what is the distribution of activation functions that were in the final networks?
They did, yeah.
There are some results. It's more in the system of thinking. It's more as in interpreting the nonlinear system that's resulting from the network. So they're trying to interpret exactly which part of the input is changed by which nonlinear activation function, and if that reflects like physical reality.
I was more interested in just purely statistics of like
how many inverses, how many Gaussians,
Yeah.
how many stuff like
What's-
that.
Yeah, if you go to figure
and what do they
7
all
in the
turn out
paper-
to be sigmoids?
Is this
And
in
you
the
say, well,
supplementary?
now let's just go to sigmoids. If like none of them had a tangent function, then you can
Supplementary.
get rid of it, right?
We have very specific, they try to interpret a specific network that's the output. So it's a very small network, so you can interpret like each node and then
Yeah.
try to interpret each node.
Yeah, about that.
But they still would,
Yeah,
they'd
this is-
still be able to look at how many different ones.
Yeah, so
Oh,
this
this
one,
is
it's a
very
little hard to see, but they have this showing you a network. And I think on the left,
So these are all the nodes in the network,
yeah.
and they color coded them by the function.
By the activation.
Yeah.
It's in this, right? Yeah, that's the only, I think, supervised learning that creates like a bigger network.
So I see a bunch of dark ones, so I assume those are inverse or tan.
Inverse stage.
Yeah.
It's-
Oh, that's one, that's two different ones.
The two together.
Yeah, it's hard to make out the
It's slightly
color.
different because one's on this screen, one's black, one's slightly.
Yeah, I know, it's hard to tell, so I'm grouping those two together. I see a bunch of those yellowy ones, but not as many. Anyway, so they didn't actually break this out.
It's pretty red, it looks pretty,
Yeah,
there's no particular pattern really.
yeah. Well, one could argue that maybe some of them never show up, maybe, like, it's interesting, I don't see a lot of Gaussians, there might be some in there, but I don't see many.
There's one right here.
I'd say I don't see many.
Yeah, true.
Uh,
Well, I don't know. I think they could just be harder to make in.
Maybe the colors.
Yeah, it's just
Yeah.
a little, it's a little misleading because you can also take, you can use the sigmoid to approximate a lot of these other things, or you can use, Gaussian to approximate some of the other stuff, so.
Yeah, that's
You
true.
can, given that they're already searching the structure, I think you can get rid of a lot of this by just having a more complex structure.
Yeah. Yeah. Okay.
So what's the results? Any other question on the algorithm, I guess?
Yeah, result. I mean, this is their main table. This is just to sort of just say that their things are working without like much training. Let's see here: random weights, random shared weights, two shared weight. Okay, so if they have if they just sort of randomly assign a shared weight in their sort of learned evolutionary algorithm, they sort of compare that with just like a fixed topology that also is given like a random shared weight like throughout the entire network, then they basically just show that fairly consistently in these three environments that they perform.
Well, the totally random one shouldn't perform well at all, right?
So this is both are previously trained. So we have a fixed one that's like trained like using like gradient descent, and we have the agnostic neural network that's trained with the evolutionary
so
algorithm.
comparing a more traditional training paradigm
Yeah, exactly.
to the evolutionary paradigm.
Yeah, exactly. And then giving that structure just all the same weight, even though it was trained with gradient descent, but then just resetting all the weights to exactly the same, and then comparing that.
I'm sorry, I missed that last piece.
They take a trained neural network using gradient descent.
Okay.
I'm just talking about in this column
So
right
they
here.
train using gradients to that.
Yeah.
They start with that.
Exactly. I'm talking about this column. They train with gradient descent, and then
That one does not change the connectivity graph. It's just changing the weights of the,
exactly, yeah.
okay?
And then they take that and they change all the weights to be exactly the same. So it was trained with, actually, I guess that doesn't make any sense.
It doesn't make any sense.
I have a different solution.
I'm sitting there going, wait a second, that's not right.
I have a different analysis. So this is like random weights in general, fixed topology and this is
So there's nothing happening there. This is
nothing happening.
this is random stuff. It's not.
Yeah, random weights everywhere.
Yeah.
It's just random shared weights, but you were explaining before. So you just select randomly across, you have like 8 options of shared weight, select one.
Can have all these come to an evolutionary algorithm?
So
No, the
this
WNN.
line is the one we're talking about, and the second one is a fixed topology. So they're always comparing this with the fixed topology.
And fixed topology means what?
It's a dense network.
Is it dense?
It's a dense
Hardly
network,
ever.
yeah.
Oh.
Here
Is that
is,
right?
if you tune just one shared weight, so you can select, you can start with a random shared, then you tune that network, you train that network, but you train one shared weight. And the last one is if you tune all weights.
With backprop.
With backprop, yeah. And what I think is really interesting here is that this is the only case that if you start a fixed topology like a dense network and when, I don't know how to call that, you get more or less the same fine results if you tune them. And in this one, the fixed topology is even better. So it doesn't mean, so if you start.
I actually am lost by this. So.
By fixed topology, you mean like a dense, a
It's a
standard
dense, yeah,
dense
we
network.
can read it as a dense. So what it says here is if you don't tune at all, you have a lot better results just learning this structure. But if you do learn, if you do backpropagate and you tune, then the results are like unfair.
Yeah, but they're very small, the differences. at that.
Yeah, the differences are small, they're like unfair.
Oh, I'm still not following. So how would I summarize this result in different words?
Okay. So if you just learn this structure,
Learn the structure through evolutionary
for
algorithm.
evolutionary,
Okay.
you have very good results. Like you can say you have 500.
And we're assuming the same weights for everybody, just with the evolutionary tuning with the activation function.
Yes.
Okay.
Then you
good results.
get these results,
You get good
515, right?
Yeah.
And if instead you train a fully dense network,
Training through evolutionary.
no, if you train through backpropagation,
fully dense network,
network, you get this result, 918.
So that's sort of their equivalent of the state of the art that we should compare against.
Yeah.
So it's not as good, it's like,
This is the state of
it's
the
like
art.
it's 40, it's 60%.
This is the structure and this is just random.
Yeah, so you get a lot better performance if you do the traditional thing, it's 918 versus 550.
Right.
Yeah.
So they're saying we're getting decent results, but only 60% of
Yeah.
what, or 50%.
And if you try a bunch of shared weights and you pick the best one of them, then you get this, which is also good.
If you did what?
If you pick
I
your
can't see what
best
Lucas
shared
is
weight,
pointing at all.
providing you pick the best,
Oh,
you
okay.
get 7, which is, so it's close, it's not that far.
Yeah.
And it's different.
So you're saying the 723 is close to the 9,
Yeah.
but it's not as good. I mean, it's clearly that's significantly less. It's not like,
Yeah, it's hard for me to know whether these numbers are, how significant these numbers are.
This is in terms of rewards obtained in the.
Yeah.
He could have normalized by, max reward.
Right, but is not, the drop from 918 to 723,
How
is that a
rapid it is?
huge drop or is that a?
it seems. to
Well,
be
this is
big.
totally random, so you can use like, this is random, this is trained. So between random and trained, you get like 1,000 reward points, you can say. And then so that, this means it's going like, 70-80% of what it could get.
Okay, so it could be like, if this was Cypher 10, instead of 97%, you're getting 75%.
Yeah.
Would that be impressive? See, if
no,
I say it that way, it's not
Yeah,
impressive.
yeah, I'm looking at it, those are pretty far apart.
That's not a good comparison in terms of enforcement, because the learning curve is not the same, it's not. So it would be more like in Cypher, that's getting 95, and the other one's getting 85. I'd put it like
All
that.
right, so it's significantly different, it's not the same, so, again, the machine learning world is all tuned about like who gets the best at anything. Whereas I think the important point here is that are there alternate ways of going about building networks?
They're not actually trying to show that their algorithm sort of matches like state of the art. In fact, in the discussion, they say that if it did match state of the art, it'd be like quite embarrassing for like state of the art. Like they kind of like made this analogy with like convolutional layers. The convolutional layers, they said, have this quote unquote like inductive bias that sort of like makes it very like good for machine vision like tasks. And so they're basically saying is that just inherently given the way how convolutional neural networks work, they end up like helping performance like quite a lot. And they're basically trying to show here is that just inherently the way how the network structures work, that help performance quite a lot.
Mhm.
They're not trying to sort of like say like are things like match state of the art.
Right. But what would be, one thing that'd be interesting is how many, in the tuned, well, in the when case, how many weights do they end up with compared to the fully dense case?
It's a lot less. And then they make the case for continual learning. Like you have
Yeah,
a lot less weights and then you can have,
Yeah, I think that's really interesting.
I think it's there somewhere, right? I don't know.
So what's really interesting about this too, of course, I mean, there's so many things going on here at once. This is not a learning system, it's an evolutionary system. And so there are no heavy like learning rules going on here, right? It's just randomly any connection, not a connection. Which actually I think is really closer to what happens in the old brain structures, right? Like when we walk, that's really the spinal cord and part of the brainstem, and we don't really learn to walk. That's a misnomer. We are programmed to walk. And so there's really not any learning going on there. We think our kids learn to walk. That's not true because other mammals just come out of the womb and start running. So this might be close to what's actually happening in like the old brain structures. But when you come to something like the neocortex, and most of the brain where we're actually learning things, those are the things that are not done this way at all. They're not. Our brains aren't set up. We don't learn through an evolutionary algorithm. So I think it's just, we have to keep that in mind when we're looking at the results. It says, yeah, this is probably how the brain learned to do these things that you're born with and that are specified genetically. But we shouldn't slide that into saying this is how we're going to learn to build AI systems. You're not going to learn through evolutionary algorithms.
I don't think they actually intend on having you like learn entire things like with this. I think they had some ideas for it, but I think like for one, they said maybe explore other things outside of gradient descent, but they also thought of these things as just sort of like existing as possible like building blocks.
I understand that. I'm just saying we can put our own interpretation on it.
True.
I'm not saying
Okay.
their interpretation.
Okay.
We have to interpret this in terms of our goals and our desires, and
Yeah.
I'm trying to put some spin on it from that point of view.
Okay.
So you know, I just think we have to understand that we just need to acknowledge that this is, you know, evolutionary algorithms are not how we're gonna build AI systems. It's useful and it's been very useful in the brain and these are pretty interesting results, but we just have to remind ourselves not to get interpreted beyond what it is.
Yeah. Okay. Trying to think how much is actually like more. I feel as we've covered like a lot of the major points.
Do they, I'm sorry, go ahead.
I mean, just, these are interesting, maybe,
Yeah.
good to go through, like this,
Yeah, true. So they try to give just an example of like, or just try to show you, you know, how these things evolve over time. And so they have this, just showing this for the, I forgot what this thing is called. I mean, they show something.
card pull.
The cart pole swing up? Okay. And so they sort of show the network at the different generations and then they sort of like show the rewards for the given weight. Basically trying to emphasize that, you know, as the generations go on, then the reward gets higher and higher for pretty much all the weights. And then you can even like play around with the sort of like, you know, input weights. But one of the things that they, yeah, I can kind of like go off. But one of the things that they mentioned is that given how small these networks are, they can kind of be interpreted. I find it somewhat difficult to interpret, but for instance, one of the things that they said in the example is that like early on, you sort of like have this velocity and you have the position of the cart, and the cart is supposed to stay in the middle. So so what they're sort of suggesting here is that the cart's off to the right
This is
side.
not a pole balancing task, this is they keep the swing up.
It's both. You have to balance the pole and stay in the center. That's the reward.
Yeah, the way you balance the pole is by like keeping the car.
Yeah, but you could stay pretty close in the center and still have the pole swinging around.
You can have, yeah,
Not
exactly.
completely, but pretty close.
I'm not sure you have to stay close to the center.
I think it said that you can't go off to the side.
Usually this task is the pole balancing task, that's what it usually is.
I mean, you can go off to the side, but I don't think it's rewarding you for.
Oh, it's not. Okay.
I'm not sure, but it's rewarding you for.
Okay, that's the normal thing, the normal thing is your goal is to balance the pole.
Yeah, and you can't go like off boundary.
Yeah,
Yeah, exactly.
if you go off boundaries, then
So I was just going to mention this sort of simple example where they basically say like, if you're sort of off to the right, there should be an inverse relationship with respect to your velocity, as in like you've gone too far and they should kind of come back in. So they sort of saying like within the early generations, it sort of like learns these connections between, you know, your position, velocity, and then like in the later generations, it's sort of like learning more complex relationships between.
do they try to interpret those more complex?
Yeah, they do. They have like a few paragraphs trying to interpret. Oh, it's getting the inverse of the velocity because of this, and that. So they're trying to interpret the resulting nonlinear systems.
Yeah. It was hard to follow entirely the arguments, but they do sort of like claim that they're.
Yes, it's getting closer to balance.
It is, yeah, but by the end of it, it's like fairly reasonable.
That's the goal.
Look at it go.
And in this case, you should be able to move the weights around a little bit and it should still do pretty well, right? Because they've tuned for that.
Yeah, exactly, yeah, so you can actually change the weight and it should, yeah, there it goes.
Yeah, it still does.
Except 0, if you put it to 0, it's like pretty.
It just doesn't do anything.
Oh, yeah, of course. Yeah, and that's why there's like this huge.
Yeah, you know, it would be interesting to run this experiment. A different thing, they're not enforcing any kind of sparsity on this, right? I mean, they start off sparse, but once they add connections, remove them, it's random, right? What, I mean, it would be interesting to say, what if you had a network that had a fixed sparsity connections, and so you can only change edges of the network. You know, you can add one, but have to remove one type of thing. And which is closer to what we do. I'm trying to bring this, you know, how could, you know, what could you learn from a network like this if you were trying to get closer to what we're trying to get to? Because here, I don't know, you might end, like here I'm seeing, I don't know if I'm interpreting this picture right, but I see this one in the right there that says Gaussian, the yellow one, and it's got all these lines coming in and out of it, and some of them only have one. So I'm interpreting that maybe incorrectly, that there's some imbalance in the number of inputs and outputs, and the network isn't, you know what I'm saying? What if you enforce a fixed sparsity network? You still allow connections to be added and deleted, but when you add one, you have to delete one. So.
Yeah.
Well, one of the objectives of the genetic algorithm of the optimization function is the size of the network. So they're trying to make a smaller network. So in some sense, they are enforcing sparsity because they're trying to optimize for smaller networks.
How does that enforce sparsity?
The evolutionary
Sparse
algorithm.
connections.
First,
How does it enforce sparsity? I mean, couldn't I have
yeah,
one unit have a lot more connections than another?
right. You can just have
So it could still be imbalanced, yeah.
Yeah.
Okay. I think I guess the last thing is just sort of, they apply this to MNIST. Let's sort of scroll down there kind of, where's the MNIST? Oh, this is them showing like the car racing example. And the car actually like performs decently well. I think pretty much a good amount of them do, but.
You can go through these examples yourselves on this website. They're kind of cool. I won't run through them.
Okay,
I mean, those, I mean, I don't want to think that these are classic examples, but they are easy examples.
yeah, exactly, yeah, these are, relatively, well, actually, the bipedal walker, I think, is like decently.
I didn't look, you didn't show that one.
I
But
mean,
both the car pole, which is really just this one dimension of movement, and the car is one dimension of movement as well. So.
yeah, I mean, they are like, there are a small number of inputs and a small number of outputs. They chose like, yeah, I mean, they are like relatively simple.
Yeah.
Did they show anything where, once they get a solution network, they try, if I remove one link, does it still perform? I mean, in other words, do they try a pruning operation after the fact?
Like a noise test, you mean something like that?
Well, with
I mean,
respect to
basically,
structure.
you get a minimal network. You say, okay, if I remove this thing, it all falls down. Okay, so I leave this one here. I remove this one, it wasn't that important. I'll leave it off.
Well, the evolution algorithm would do that, right? So.
Do they ever actually delete connections in the evolution algorithm, or they just add?
Oh, that's a good question. I don't think
Oh.
they didn't mention that they do actually.
Oh, really?
They just said that they add in.
Right, so
They add it
once you get a
minimally.
solution, then you can
Oh, well, I'll
say,
take
okay,
it back one step.
Yeah.
I assumed that they deleted them as well as added them.
No, they don't. They just start with very small ones. That's a good point.
That's a good one. So you'd end up with, you'll almost certainly end up with ones that aren't doing anything.
yeah, with an overcomplete network.
Yeah.
Yeah, but you can just, whether you want to do that dynamically, or whether you want to say just all in until I get a solution, then.
So that goes back to my suggestion. It would have been really interesting if they ran it with a fixed sparsity, and so you don't start super sparse, you start with some level of sparsity, and you if you add one, you delete one, you add one, you delete one. And in that situation, you would think you wouldn't end up with much that wasn't useful.
Yeah, but if you do that, your chances of getting to a solution will probably be a lot slower.
It's not clear to me. It's interesting. You might be right, but I think that's why it would be interesting to run the experiment. It's, what you end up here with, this sort of a very highly customized solution where you have every node has a different number of connections, and every node has a different activation function. And so you have this almost like handcrafted solution, or evolutionary crafted solution, whereas if you force yourself to have a single activation function and a certain type of sparsity, then you're sort of exploring a different part of the space of solutions. You're restricting yourself to like, okay, given sparse connectivity networks of a certain sparsity, what can be learned and what can't be learned. Again, I'm thinking ultimately in the future of AI, we believe that these things are going to be sparse and they're going to be relatively fixed sparsity. And it's more, for me, our purpose is more used to understand the limits of that, not the limits of what you can learn through an evolution network.
Yeah, I think there's like two scales on this, because at one level, there's only, if you're looking at the biological model, there's only so many connections you can make in a certain area for a variety of reasons, but it's still very robust. On the other hand, on a larger time scale, where you have things in the cerebellar cortex and various other places where you have all these connections, and you're kind of over time pruning them away, you have this rich network, but by various means, you're kind of removing elements from that. So I think there's both mechanisms can be operating, that you're working against a constraint, which is kind of what you were describing, and saying, I can only make so many connections, it's a trade-off. There's another one where I say, I've got a very rich space, but afterwards, do I really need all this all the time? And then, I think both of those mechanisms could be in operation.
So these are the MNIST
Yeah, so this is evidence results. The idea, so just before we go on the table, they were talking like in a reinforcement learning, but they sort of also wanted just to show that it's actually like a reinforcement learning setting where there's a small number of inputs and a small number of outputs. But they also wanted to show it could like work in like a supervised setting, such as MNIST that has like a relatively larger number of inputs, and you know some high number of outputs, or at the very least a high number of inputs. So they trained like in a very similar way their evolutionary algorithm, and just from the evolutionary algorithm they get like 82% accuracy, which is much better than chance, right? Are you laughing?
I don't
Okay.
know. It just makes me laugh. It's like, it's like cue that laughter.
Okay.
20 years.
Let's see here. Okay. Yeah, I was using MNIST. Okay, so they also ensemble weights, so they also train like so they take that same network and then notice that it can sort of perform. Where'd it go? So they take that same network and then notice that it can perform. I did?
Yeah.
Okay, yeah. So like this like one network, if they sort of like look at the classification accuracy for just different weights, they notice that this is MNIST again. So this is like the digit, and then this is the like the weight value, sort of like the shared weight value after the training has been done. And then
Stay away from zero.
the yellow is the percentage. So they notice that the sort of like accuracy is different for different weight values for different digits. So like for one weight value, that may just be better suited for one digit, and for another weight value, that may be suited for another digit. So in a sort
It's
of
weird, isn't it?
So what they do is they sort of like make like this ensemble where they sort of kind of like take the best weight values of every single digit. So then they have an ensemble of 10 networks that sort of are better tuned for like one digit. And then they sort of have that ensemble like vote. So essentially, the weight value, the network with the, for digit 0 will vote, and maybe it will vote for like a 0 for 3 sometimes, but it will still like vote for 3 quite a lot. And then it's just sort of like whichever digit gets like the highest vote. So I'm trying to like describe how their ensemble had worked, but they essentially use their.
Isn't this like random bars or just standard? I mean, this seems sort of orthogonal to the point of the paper.
It is. They're basically. It's kind of it is decently orthogonal to the point of the paper. It just is sort of like say like if they train this ensemble, then they get sort of like matching test accuracy if they just did like use like linear regression. So that's kind of interesting. So basically say like, just one weight alone, sure, that may not do it, but if you take like an ensemble of the weights, then you can sort of match it.
Yeah, I'm saying, so it's orthogonal in the sense you can take any system for learning MNIST and say, oh, I'm going to train on for each digit and do an ensemble loading, and I'll get better
Yeah.
results. It's almost guaranteed.
Well, they don't train it for individual digits.
No, but
Yeah.
they evolved it for individual digits, and they chose the one that worked best.
No, they evolve one, and then they pick
Yeah.
one weight for each one. So I mean technically, like the train, you're right. It is like a training that's done.
They end up picking different networks, one for each that seem to be tuned best for one digit, and then they're doing ensemble loading.
Yeah.
I mean, it's not a bad thing to point, but it's not very significant in the sense that ensemble loading almost always gives you better results no matter how you go about it.
Yeah, that's true. If anything, they're just trying to show like the sort of application to the supervised learning setting. And if they take that one network trained with the evolutionary algorithm and just sort of train, all the weights, so it's a sort of like a minimal network and then train all the weights, then they get this 94.2% accuracy. The only interesting point about this is that they point out that the paper, deconstructing the lottery tick hypothesis, which I haven't read that, but
It's gonna be the beta.
exactly, it's going to be in the next
Just an advertisement.
But they thought so, in that one apparently they sort of like learn by pruning, I think, some sparse mask that sort of goes over the network, and then once a sparse mask is used, then I guess sort of irrespective of the weight, then they get around like 94% accuracy. So
84.
Oh, what is it?
84.
Oh, is it? So what is this then? So I haven't read this paper, so I mean, but I did sort of like look up this one thing. So the learn mask. Oh, I see.
Oh, with the initial weight. Yeah.
Oh, okay.
Yeah.
Okay.
No, it's supposed to be 84.
I can ask her.
Yeah. True. But they just find it sort of like interesting that, you know, kind of taking these different routes of like trying to like learn minimal connections, you end up like with roughly the same accuracy.
I have a question there. Well, why is it one way performs better than an ensemble way? Oh, okay, you're training that, all right.
Yeah, exactly. Yeah, with the ensemble.
Okay.
Yeah, yeah.
You're training that.
Okay. Yeah, so that's it with the MNIST thing. But these are just sort of like summarizing.
Just dropped like 10 users.
I think that's all like the
10
results,
viewers, I
the
don't know
major
why.
results
So
that
if
they
anybody
actually
has
have
any
in the paper.
problems, we just report in chat.
So if you take their method of creating the structure and then train that with backprop, you get 94.2%.
Yeah, exactly. Yeah.
And that's not really very impressive.
No, it's not.
But it's a much smaller network, and I think they could make the point that this resultant networks are a lot smaller. But I don't see a lot of that showing in the paper. It gets to 94, but how many parameters does it have? I think it might be like in the order of, I don't know, 5-10% of the 99% network. I'm not sure.
Yeah.
Is that somewhere, like the level of
The level of sparsity.
parameters for each?
Actually, where you were just a second ago, they mentioned something about 1,000 weights.
Tell me here.
Oh, there,
In the,
1,048. But what about compared to the fully connected? It says 1,849, right?
Connections, yeah.
What about the fully connected?
well, in the table, what I'm trying to do is get you back to where you had the table,
There was you're talking about over here.
where they had the table comparisons.
The table.
Yeah, right there.
Numbers. Okay, so, yeah, so it says, as well as a linear classifier with thousands of weights.
Right.
So it's actually multiple weight values. So I'm probably trying to imply that they're much less than thousands of weights.
Right.
In the legend of the figure.
Yeah.
Yep, thanks for coming back, folks.
Right here.
Yeah, the last few words.
Okay, thousands of, yeah. I was curious, like how many?
Yeah.
Yeah, I don't think it's too much.
It can be like 5%, 1%, 10%.
No, I understand that that's not definitive. I'm saying that's their swipe at it.
Yeah, I think with the dynamic sparsity stuff, we're trying to learn the connections then, as a part of the core part of the learning. Just like, and then similar with temporal memory. You can think of temporal memory as being a weight agnostic structure. It's all about the structure, but the same activation function everywhere and binary weights. We've learned the structure as part of learning. It's an evolutionary system.
What about, okay, we can talk offline. I have
Yeah.
more questions.
Okay. Yeah, well, I guess that's about it. Personally, I just had the motivation of going through this paper because, I mean, for me, it wasn't immediately obviously coming to Numenta that there was like a lot of importance in the structure. So like this in combination with the lottery ticket hypothesis, your eyes pop up. I mean,
Everything we've done here for years is based on structure, so it's like to say that it's surprising.
No, I'm not saying that
It's
sounds
not
like
surprising
surprising.
to me because I think that's true for 99.99%.
Yeah, but we're here, this is Numenta, right?
Yeah, I know, but he
So-
wasn't in the mentor.
I know, but he's here now, so we gotta all get on the same ticket here, right?
Wait, he said before he came to Numenta.
Before he came.
Okay,
Yeah.
all right.
I also-
I
I also want to differentiate between like surprising and just sort of like, I don't know, I guess, I shouldn't say necessarily surprising, but just sort of like actually sort of getting the sense that like feeling that it's actually like intuitive, that it's sort of like a matter of fact as opposed to like, oh yeah, this is like plausible. So I think like in combination of this with the like lottery ticket paper, I think it just sort of, at the very least reinforces the kind of stuff that Lucas and I are working on the dynamic sparsity and obviously the stuff that Numenta does as a whole. So at least for me, from my perspective, sort of like understanding this is kind of nice to help me understand sort of things here in Numenta in a broader sense.
And it's good that supports our hypothesis.
Exactly.
In the level, right? So all these papers, like the constructing lottery ticket and this paper, they're all supporting the hypothesis that we are bringing to machine learning community, that the structure matters.
Yeah.
So it's just personally frustrating for me is I don't view this as a hypothesis.
Oh.
Right? I mean, it is inherently obvious to me, and I can walk through the logic of it, and it's been that way for decades for me in some sense. And yet, it is still difficult for other people to come to agreement about this. And so, so part of my angst here today is this dealing with this. It's like, oh my God, we're still talking about whether this is, these issues in my mind have been resolved a long time ago. And I'm not expecting, that's not a criticism, it's just an observation. I have to figure out.
This could be a good topic for a Distill article, I think.
That I don't want.
I think one thing to come away with some curiosity about is that if there's a formalism that allows you to abstract the learning, whatever, this percentage in this particular topology is due to the weights, this percentage is due just to the connections. If there's a way of actually saying, yeah, you can do it all with one and you can do it more or less all with the other, but is there a way of manipulating these things as two abstractions toward, a common
Yeah,
goal?
that's
Yeah,
a
I
good
mean, in
point.
the neocortex, it would be almost 100% structure.
Yeah.
And by the way,
It's a very
that comment, that in the neocortex is almost 100% structure, it's not a fact, because synapses don't support weights. Synapses are unable to support even 1 or 2 digits of precision. They are like binary, and the only thing you can do is you can turn them on, turn them off, grow them, get rid of them. So this is an observation made many years ago, that it's fundamentally inconsistent with the idea of weights. In the minimal, it's a very, very small amount of tuning you can base, they're like binary. So one way you could say, well, maybe that's not the best way of building networks. Maybe the best way of building networks is to go with weights and for synapses, and that may be true. But from my personal philosophy point of view, is I found that if you start exploring the space of possible solutions for intelligence, you just run into morass and never make progress. Where if you constrain yourselves to the biology and just accept that's the fact, then you won't get lost along the way. You won't go down rat holes where you're exploring different activation functions randomly. You just say, I know there's a solution in the brain is constrained by this, let us completely understand how the brain works first, and then we could ask ourselves, after we understand that, we could say, oh, well, could I improve upon that? Could I improve upon that, what nature's discovered, how to build intelligent brains, by adding something else? But in the meantime, if you do that now, you just get lost, and that's why I believe the AI has been very unsuccessful in its stated mission since the beginning. And so that's a sort of a philosophy point of view, and it's been borne out for me over and over and over again. That's the founding principle here at Numenta in some sense.
Okay, on that note.
And that lecture.
Okay, you guys,
Well,
you want me to
thanks,
turn off the stream?
Yeah.
Okay, thanks for the meeting.
I think that's very relevant.
Okay, you're offline now. Okay. So, you guys, thanks for watching. So one of the main things here that I want to, hold on, I gotta turn this off, or all I can hear is them. So weight agnostic neural networks are similar to how the temporal memory in HTM systems is weight agnostic. That's one of the